Everyone. We're going to be talking about radiation surveys in this presentation. It's important to just have a full understanding of the difference between radiation and contamination because you can survey for both of them. So the radiation is just the pure energy that's in air, whether it's coming off of a source, coming off of a radiation producing equipment. It's seeking to quantify the levels of radiation in the air. And that's contrasted with contamination, where you're actually surveying to see if there is or is not radioactive material present. It's essentially contamination is radioactive material where you don't want it, and that way you would use a different type of instrumentation to verify that. So there's different methods of protection from radiation versus contamination. From pure radiation, it's the usual time, distance, shielding. Those are the three main strategies for keeping your doses as low as reasonably achievable. That's that ALARA strategy. So you minimize your time around a source, you're going to get less radiation. You maximize your distance, that is a significant dose savings. And finally, just using shielding. Versus contamination, where you may have radioactive material somewhere where you don't want it, where you don't even know it's there. So that's where the standard gloves, potential face mask, lab coat, all those things protect you from that accidental contamination that could potentially get on your skin, give you skin dose. It can get on your hands, lead to ingestion. That would give you that internal dose, that committed dose. So the strategies of protecting against contamination are really just good, hand hygiene and proper protective equipment. Personal protective equipment is the PPE. So there's really two different types of areas that you have in mind in a licensed facility. You have controlled versus uncontrolled. So, as the name suggests, you control access to the controlled areas. Versus uncontrolled, MSK is a hospital. We have lots of members of the public coming through. We still have responsibilities for these areas to keep them very low in radiation, low in potential contamination, versus a controlled area. I know that uncontrolled says it's not under the licensee's radiation protection program. That's not completely true, because we do have a lot of things that we do in uncontrolled areas, but generally the controlled areas are where we have, patients with dosimeter, or not patients, we have staff with dosimeters. We have more active therapeutic uses of radiation, higher levels of radiation. You have higher limits for levels of radiation, because in theory, there's only occupational workers there. There's no members of the public in these areas unless they're there for a reason like receiving therapy. Yeah, so controlled areas, you want it to be secure from unauthorized access and unauthorized removal. So you just want an area where you can be confident that big 10 curie HDR sources are not going to go missing, or someone's not going to randomly walk into a Linac vault and get a large dose from a treatment that's happening. Like that seems very far-fetched. And the reason that's very far-fetched is because they are controlled areas, because there's staff around, because there are lots of barriers to entry for the average person. So we talk about design goals for controlled versus uncontrolled areas. Again, we have to go back to those dose limits. Member of the public limit is 100 millirem in a year. So really where you get the weekly limit, which is a design goal, generally you hear in millirem per week. So if you take 100 millirem in a year and you divide it by roughly 50 weeks in a year, that gives you the value of 2 millirem in a week. And that's a very important value to remember, especially when it comes to shielding. When we're discussing shielding, probably in the fall, this is going to be important for you to remember that it's 2 millirem in a week. And again, if you remember that 100 millirem limit to members of the public, then it's pretty easy just to get to that 2 millirem, remembering that the roughly 50 weeks in a year. Now, on the occupational side, goes hand in hand with the controlled areas. You have the worker limit of 5,000 millirem in a year. But for two reasons, we don't go for that value. One is that you could potentially have pregnant staff working in these areas, and the limit for a pregnant worker is going to be 500 millirem over the course of the pregnancy. So you want to design for that potential pregnant staff. And also you think about that, again, that ALARA philosophy, as low as reasonably achievable. Just because you can get that 5,000 millirem a year doesn't mean you want to be in a controlled area where you are consistently getting 5,000 millirem. So that's why it changed from the design goals changed from that 5,000 milliram a year, which would work out to about 100 milliram in a week. And they changed it to the design goal of 500 milliram in a year, which works out to roughly 10 milliram in a week. So that 10 milliram in a week and 2 milliram in a week are weekly design goals for areas that could potentially be exposed to radiation. So if you have members of the public, you want that 2 milliram. If you have occupation, you want that 10 milliram per week. And we will again cover this when we talk more about shielding. So you have all these numbers, you have all these goals. You need to actually go out with a meter in hand and measure the radiation in these areas. So that's what we do a lot. That is a big part of what our group does. We will confirm shielding. If there is a shield area that is shielded, we confirm that it is shielded to the correct attenuation of the radiation. So there's no unsafe areas, no areas that are at risk of overexposing people. One of the most common surveys we do are surveys of patients. You give a patient a large dose of radioactive pharmaceutical and you want to know how radioactive they are. That dictates how many precautions you give to them. So they then, if they're going home, they're not going to irradiate their family. They're not going to irradiate members of the public more than is necessary. So a lot of times we will take measurements of these patients either once and then let them go, or we can take measurements daily for a couple of days if they're in-house for them to get to a point where they can be taken off of radiation isolation, which is essentially no more radiation precautions for them. So the nurse, that changes procedure for the nursing staff, for the physician staff, for housekeeping, there's just a lot of things that revolve around the patient being either in radiation isolation or not in radiation isolation. So that's something that we take regular surveys of to track that slow decline of their dose rates. And finally, these patient areas, these are going to be surveyed on a regular basis, both for contamination and radiation levels. For something like a LINAC vault or just a basic X-ray room, we have to confirm the shielding design and the effectiveness. It's all theoretical until it's physically built. Larry Dower, the RSO, is in charge of actually designing these facilities, and he has, there's programs. There's other ways to verify that you're doing. You design in safety factors, but ultimately you really need to make sure that it was built correctly. You could have the best design in the world, but if it's not built correctly, it could be a hazard. So we need to take these dose rate meters. Anytime a new machine goes into a LINAC vault, anytime a new LINAC vault is built, we run up, down, left, right, and anywhere that anybody could physically place themselves around these vaults, we will take dose rate measurements to make sure that there is not any excess levels of radiation that could be out of compliance or just a general hazard. A lot of machines, you'll have times where they put out very intense radiation, and you can get large numbers. You can get that, you can go well past 10 milliram per hour. But remember, it's 10 milliram in a week. So if you have a dose rate of 100 milliram per hour, you might think, oh, well, that's going to, that will give them 100 milliram 10 milliram in a week very quickly. But if that machine is on for, seconds at a time or minutes a day, then it's very possible that you'll never actually reach that hour of irradiation. So you have to factor in what is known as the occupancy, the use factor, and the workload. So again, this is going to be covered very extensively with shielding, but just as a little preview, occupancy is how much are these spaces actually occupied by people. Use is how often are these machines pointed at a certain wall. So, the LINACs rotate 360 degrees. They're a very intense, very directed radiation. If it's pointed at a wall versus away from a wall, it makes a very big difference in the actual radiation present. So that's another factor. And then finally, just the workload. That's just beam on time. These beams are on for a small portion of the time that they're occupied. So you take that into account, and that lets you really reduce the realistic amount of radiation that would be present over the course of something like a week or something like a year. And this work is supposed to be done by a quote-unquote qualified expert. That's someone that's licensed by the state of New York. A lot of our group is not licensed. It's a pretty extensive licensing process, but we have licensed experts that do sign off on it. So we're in compliance on that aspect. X-ray shielding for a standard, GenRad room is a little bit less extensive, but there's still a lot of design considerations. You want to have the room set up in such a way that the person actually turning on and off the X-ray machine has protection not just from the direct radiation, but also from a single scatter radiation. The more that radiation bounces around, the more it'll give up its energy, the less intense that photon flux will be. So you want to design a room where the person is behind shielding, but it can still be open on a side as long as that side doesn't have direct scatter access to the radiation coming from that machine. You also shield typically to 7 feet from the floor. The thought being that any other direction, if it's going up or going at an angle higher, it's not going to be hitting people until much further distance. And again, when you talk about that inverse square, how radiation falls off with distance, even adding a little bit of distance can really bring those dose rates down. So typically this is just to save money, is you don't want to shield anything that you don't need to shield. So 7 feet from the floor is typical for a GenRad room. And you can see that the common thicknesses of lead that are used, it's dictated by the energy of the radiation. So for diagnostic, dental, and mammo, those are low energy machines. So typically a 1/16 of an inch of lead is more than sufficient to protect those rooms. But then you talk about CT, and that gets into a little higher energy. So typically it's a little more intense radiation source as well. So that's where you get up to like the 1/8 inch of lead. And then we haven't talked about PET CT. When you factor in, 12 millicuries of F18 per patient, those photons are going to be much higher energy than even the CT. And that's typically where you see 1/4 to 1/2 inch of lead for these rooms, just because of that higher energy. You really need more lead to shield with it. And so this is a little excerpt of one of our surveys. You can see typical dose rates for a CT alone. This is MR per scan. So if you're standing right next to the CT as it's going off, you can expect to get about 10 milligram. Not a huge dose, still something you want to avoid. It's very common for us to get frantic calls from somebody that says, oh, I went into a CT room just as it was starting to scan, and I'm afraid I got a dangerous level of radiation. So, rightfully so, that person is a little concerned. But we can go back to surveys that we've done on the machines and say, okay, well, where were you when the scan was off? They say, oh, I just entered the door and then I immediately left. We can say, okay, well, we have a survey of that rough location, and you were exposed to about an extra 0.3 millirem if you were there for the duration of the scan, which usually they're not. So it's a fraction of a millirem from this type of exposure scenario. Usually that makes them feel a little better. If they're still, on edge, we can get their dosimeter, an emergency read, and it'll show that there was no recordable amount of radiation. So we know that what to expect really from a dosimeter read, but it's useful to have these surveys on hand for a situation like that. Then I talked about PET CT. So that ups the radiation dose, just because you have that person on the scanner as a radioactive source themselves. 12 millicuries of F18 will put off, pretty significant dose rates for a period. So you can see that, okay, combine the CT with that PET dose gives you a little bit more dose close to the person, close to the machine, but still on the doorway, you're still going to get very low levels of radiation exposure. So this is an MR per hour with the PET doses. So when you sum the two, you're not going to stand next to the machine for an hour, but you will get a little bit of dose from that F18 in addition to the x-rays from the CT. Still a very low exposure scenario. So a lot of times we are looking for contamination in our surveys. There's a lot of daily and weekly wipes that we have to do to make sure that areas are free of contamination. A lot of this is in the labs. Also just, the treatment areas are very liable to have small amounts of contamination. Patient rooms, if we treat an in-house patient with, a Curie of I-131 and they stay in that room for 4 or 5 days, there's going to be little amounts of iodine everywhere, especially in the bathroom. But there's areas where you expect it. Contamination is really where you don't expect it, where you don't want it. So we know that there's going to be iodine in the bathroom. That's not surprising. We still want to survey for it and clean it up. But we're more concerned about areas where people don't expect it. outside of the room, on the handle going into the door, something that's going to be used by a lot of staff. That would be an area where we don't want contamination. We would survey for that to make sure that once that patient leaves, there's no residual radiation that can affect the next patient coming in, can affect the staff going forward. So that's why these surveys, whether with an actual handheld detector or taking a wipe test and then counting it, are very useful for keeping staff safe. There are other examples like package receipt. Whenever we receive a radioactive package, the regulations say that that package needs to be wiped for removal of contamination within the first 3 hours, within the first 3 hours after it arrived. So every radioactive package that comes into our facility needs to have a wipe on the outside, make sure there's no removable contamination. So that way anyone else that ends up handling this package doesn't get any of this contamination if it is there. A lot of times, if there's a lot of contamination on it, that's a reportable event. You report it to the regulator, and there will be a whole investigation with the shipper, the trucks they use to move it. And every now and then you'll hear that, there was like a source that spilled and it contaminated pretty much a whole supply chain. But usually if there is some contamination, it's very low levels, below reportable quantities, just something that for your own knowledge, your own safety, you would record and then mitigate in your own way. We haven't talked about instrumentation yet, which is tough. Usually that comes a little bit earlier. But since we're talking about surveys, it's important to understand that depending on what you're looking for, whether it's contamination or actual radiation levels, your instrument is going to have a certain level of efficiency, which is pretty much just says how good it is at detecting the radiation in question. So some efficiencies can be, 20 to 40%. If something is 50% efficient, that means it's getting 1 out of every 2 bits of radiation that actually hit the detector. 50% efficient is asking a lot. I've talked about how measuring equipment, instrumentation, and radiation safety and health physics is very difficult. If you get something that's 10% efficient or even 1% efficient, sometimes that's a very good efficiency. But the main thing is that how efficient your instrument is for the situation you're attempting to quantify, whether it be radiation or contamination. And it's part of the calibration process to give efficiencies for certain energies of radiation, certain types of isotopes. And that really helps you make those in the field calls to know what's there, because you can get a click rate, counts per minute, but you need to have some other information to know what that equates to in terms of actual real world activity, which would be this disintegrations per minute. That's an activity, or an actual dose rate. So there have been a couple of events that have happened, some serious events where people start to take apart big equipment. A big one is cobalt teletherapy machines. You hear from time to time that the head of a cobalt teletherapy machine ended up in a scrapyard, and it looks valuable. So you have people that attempt to break into these machines to get at the valuable metals inside. Every now and then, there will actually still be a source in it, and so these people break in. They see this cobalt, this blue metallic source that looks valuable, and they'll put it in their pocket, or they'll bring it home, or there's 2 cases here. This actually, the hyperlink down here, if you want to read about it, is a case that happened in Thailand, I believe, and then there's one that happened in Mexico. But the idea is the same. It's a cobalt teletherapy unit that was discarded, sold for scrap. Cobalt still inside. Someone grabbed the cobalt and ended up getting very sick or potentially dying from it. And the reasoning for that is that there are markings, but if you don't have familiarity with this marking or caution radioactive materials, if you don't speak English, this may not mean anything to you. So that's the idea of, you can take these surveys, you can know it, but you also have to communicate what you find with these surveys. Most of the hospital is looking to us to come with a meter, to take a reading, and to communicate something to them, whether it's a risk factor, just a straight dose rate, just a straight click rate, or they want more information. It's on us to communicate the findings of that survey in a way that the staff can understand. That's one of our jobs, one of our main jobs in the hospital. But this is not just limited to us. This is a concern in the broader radiation sciences. How do you effectively communicate risk to somebody that may not speak your language? And actually, one of the ways that came up, this is a concern that goes to the waste on the other presentation we're talking about this week. How some of the waste coming out of these nuclear power plants will be radioactive for tens or hundreds of thousands of years. And they could be incredibly hazardous, like to the point where it could still kill you or cause serious harm down the road. So there's been this thought of, how do you communicate to a potential human living on this earth 100,000 years from now? It's almost impossible to fathom what that will look like. But they want a reliable way to make sure that when they stumble across this stuff, they know that it's hazardous. And that's where this red sign has come. And it started to come into use for the situation, like not speaking a certain language, trying to communicate that this source is deadly. It contains some sort of radiation. You don't need to know this is radiation, but if you open something up and you see this, it should do a pretty good job of letting you know that there is something that is dangerous here. It's pretty much saying there's radiation that's going to kill you, get away. And I see that. I don't know if everyone would understand that, but this was what has been accepted as that universally understood sign of something is hazardous here, get away from it. And so I think that this has slowly been phased in as a method to avoid situations like the two listed here. But for less high stakes situations, a lot of times we do have postings for ourselves, for postings to communicate this information when we are not physically present. So you'll see some of the signs here. It's difficult because it's in language that is easy to accidentally use. I myself very often will describe, a high reading as very high radiation, but I have to correct myself to keep in mind that very high radiation has a very concretely defined value. So you shouldn't be using any of these terms unless they actually apply to the situation at hand. So caution radioactive material, if you actually look as you walk through the hallways, you'll see this everywhere. MSK posts this on a lot of areas, even if they don't have active radioactive material use. It's just seen as, I guess, something that's kind of prudent to do. I don't know if I agree with that. I think it should be a little bit more specific to areas that are actually using radioactive material. But I think it's a compliance issue to try to avoid an inspection where we get dinged for something as simple as not having an area correctly labeled. So you'll see caution radioactive material a lot because we use a lot of radioactive material in the hospital. Now we get down to, that is just physical materials present. This 10 CFR 20 Appendix C value, that's just a value that says that that material needs to be licensed. You need to have a license in order to have that material. The rest of them are just signs that would communicate levels of radiation present. So if you were entering a radiation area, you know that that area has levels of radiation that are above 5 millirem per hour at 1 foot, or at 30 centimeters. 30 centimeters is roughly 1 foot. So that's where you would see something caution radiation area. Something high radiation area. If you have caution high radiation area, that suddenly bumps up to an area that has been recorded as having over 100 millirem per hour at 30 centimeters. So if you saw that sign, that would have a very specific meaning of over 100 millirem per hour. And then very high radiation area, this is something you don't see very often, thankfully. But for us, or just for a definition, that is greater than 500 rad per hour at 1 meter. So if we go back to thinking about deterministic effects of radiation, 500 rad is about that 50-50 level where you have a 50% chance of dying if you're exposed to 500 rad. So that's a very, very serious posting. And it's interesting to note that this is in millirem, this is in millirem, this is in rad. So this is dose equivalent, which, remember, that equates to potential risk for effects down the line, whether an elevated risk of cancer and the like. Rad right here is used as absorbed dose, because if you're in a very high radiation area, you are not concerned about potential risk for cancer. You are concerned that you will face very immediate effects from this radiation if you were to be there for any extended period of time. So that's why they go by absorb dose. That's just, they're looking for those deterministic effects. If you stand here too long, you could get, you could get significant blood changes. Your hair could fall out. You could very well die if you spend too much time there. So that's why this one is defined as a much higher level and defined using a different unit, just because of the different type of risk. So these are values that are important to memorize. Hint, hint. Unfortunately, there's no way around just memorizing what the values are. So we'll try to work on, seeing those more than once. There are some exemptions to those posting requirements. Sealed sources that are less than 5 millirem per hour at 30 centimeters, you don't need to post at all. You don't need to post caution radioactive material. Radiation producing machines, because they are on and off, they're only on for such a small period of time, have different posting regulations. Patients who are released in accordance with regulations, so they're released with certain precautions and such, don't need to have postings. And finally, just if you're sending a package that has a high radiation level, you don't need to post while the package is there, because in theory it'll be picked up shortly. So a posting would not be necessary. So if you have a high radiation area, remember that's that above 100 millirem per hour at 30 centimeters, you would need to have a physical barrier preventing people from going in. So you can do that in a number of ways. You can either directly surveil the area, know when someone's in there. You can keep it very locked in a way that no one can get in because only you contain the keys to that lock. Or you can have it in such a way that there's some sort of interlock system that if someone was to enter, the power is cut to the machine and there's no radiation source possible. So that's how we operate the LINACs. If the doors are open, there is an interlock that prevents that machine from being turned on. And that would be a successful way of controlling access. And then finally, if you have these controlled areas that have high radiation, how do you keep your doses low from contacting you, from going in these areas, from being around these areas? And nothing changes. It's time distance shielding. If you want to keep your doses low, don't spend a lot of time in there. If there's one large source in there that's causing this, you can move it further into the room. You can shield it. It all comes down to time distance shielding. It's no different if it's a posted area versus a non-posted area. It's just a controlled area is much more likely to have these high radiation areas or very high radiation areas. So it just makes that time, distance, and shielding that much more important. So that's it for surveys. Really just taking home the point that you not only need to quantify what's there, whether it's radiation or contamination, you need to have an effective means of communicating it. And that's where the postings that you see will come into play. So we'll talk about it tomorrow. Thanks.